definitely love having him here working on our safety projects as well. So at this time, I'd like to kick it over to Stephen. Thank you, Stephen.
All right, thanks for the introduction, Eric. Can everyone hear me correctly? Yeah. I think so. Yeah, that's me. I see my microphone. Yeah. All right. So before we dig in real quick, I want to give a brief introduction as to what GCAPS is. There's a lot of acronyms in the umbrella of VTTI. So we are the Global Center for Automotive Performance Simulation. We're an affiliated company of Virginia Tech. We're a nonprofit based in Southern Virginia. And we started out much as what Eric had laid out, doing tire testing, vehicle testing, and then we started doing simulation for tire models, and that sort of opened the door to this broader automated vehicle environment, and we've been growing ever since. And yeah, we're aiming to get deeper into the mobility industry as a whole, and different OEMs, and yeah, it's sort of a quick background on GCAPS. So on to the presentation at hand. We'll be covering the ADS sensor degradation to testing, modeling, and detection. So a quick introduction to the project. The sponsor, Commonwealth Cyber Initiative, wanted to explore ways to combat potential misinformation that would be sent to the sensors of an automated driving system, whether that be hacking or something malicious or just bad data from a sensor. So the project goal was to develop a sensor degradation detection algorithm to be used in simulation. VTTI provided the data from their naturalistic driving database. We used to recreate those scenarios for the simulation environment. They also provided test equipment and facilities to collect the sensor data that we used to build and validate the sensor models that were operating within that simulation environment. We developed a virtual framework to test these various sensor states and then evaluate the response from the detection algorithm. And the additional major outcomes were we've developed a process for collecting the sensor data in operational environments using functional tests. We created these statistical sensor models, and then we also showed the capability of using a simulation environment to increase the development of algorithms outside of testing an inordinate amount on the road at cost and time expense. So moving forward to the project structure here, we've got all of these tasks laid out, and they sort of group together into these three main subgroups. So the first group is the simulation tasks. So we start there with the naturalistic driving database. We downsample to a specific number of scenarios that we want to recreate and parameterize for the simulation environment. We then randomize those scenarios so that we can expand the list of test runs to generate data. So for example, we might take a near crash event, change one of the parameters like lane position, and suddenly it becomes a more traditional baseline type event, and completely change the output of what the sensor response is. And from there, we're able to simulate those recreated events, and we do that within CarMaker. They've got a fairly robust list of sensors that we can use to capture that environment data within the simulation relative to the sensor specifications that we apply. And that leads us on to the sensor modeling tasks, where we first collect some development data using actual sensors on the VTTI smart roads. We evaluate that, extract the objects, and build statistical distributions of the different noise and errors that we see in the sensor data, both as a baseline and relative to the degradations that we apply. And from that, we build a statistical model, layer all of these distributions that we see, and then once we have that, we're able to feed the simulated sensor data through that to generate degraded sensor data at various levels. And once we have that, it's onto the misinformation detection algorithm, and we were able to use the perfect knowledge data from the simulation environment to sort of cross-reference and validate the algorithm. So with that, the major project structure broken down, we'll start with the simulation tasks. So first off, we had the naturalistic driving data selection. We knew this would be a very effort-intensive task, so we limited ourselves to 100 events to recreate from the NDD. We selected for rural, highway, and urban environments to cover our bases, and we parameterized data according to these parameters that are already part of the NDD. So event severity, crash severity, incident type, weather, road alignment, lane occupancy, and traffic density. So you can see a handful of these. For example, weather, a lot of them stack up in just one bin, being no adverse weather conditions. So the distribution of this data is not entirely uniform, as you might expect. And if we want to capture the full space, all the interactions between these different variables, it would expand into have their 500,000 possible combinations in the factorial expansion. So it's just entirely unattainable. So we need to go through and try and find a way to select for the scenarios that are most meaningful. So when we plot the different distribution of those combinations, you can see they mostly stack up all in one, like I showed before. And there's a grand total of 1,078 unique combinations that were in the data set. And from that, we still need to pare it down to get to 100 events. So we tried looking at different ways to select for the uniqueness. So we have here the different pairwise interactions. This is only one way, not the multi 7-dimensional graph. So you can see there's a handful of colorful spikes. That's the major, most common event types. And then there's a lot of these dark blue scenarios. Those are the tails basically in the distribution. And so what we want to try and do is capture both the peaks of the distribution, but still maintain all of these different interactions that we see here. And when we try and capture just the top 100 events, or maybe try and match the distribution, we lose a lot of these dark blue interactions between the different parameters. So we came up with a method to select for that variability while maintaining the distribution of these top line parameters. So what we did is we defined this variable distance between the different combinations. Basically, these are all 1,000 events plotted against each other. So the diagonal is obviously 0. They are one and the same. They have no difference. And then 7 means the variables are completely different. There's not one that's the same across them. So From this variable distance, we were able to rank them all according to how many of the different events have an event that is only one variable change away from it. So you can see this one event here has maybe 30 or so events that only has one change difference, and maybe rain to no rain, but all the others are the same. So we developed a little algorithm to go through and select the most prominent of those one-way combinations, and then iterate through finding both the most dominant, so those colorful, the bright spots in the graph we showed previously, but it's also maximizing the breadth of data and combinations that it's trying to match against. And so we're able to go through and reduce that list down to here shown in green, about 200 events. And then from there, we ended up selecting the top 100. As you can see, most of the tail end here only had one or two events per combination. So this allowed us to get a broad distribution of data while maintaining the peaks in the data that we saw, distribution data that we saw. So that was the selection of from the naturalistic driving database, and then we needed to recreate these scenarios. This task, we used Roadrunner in MATLAB to take all the data sets, the video, the GPS, combine them together to create all of the vehicle trajectories. We likewise decoded the environment to create the simulation space and combine them into an open drive file that can be used within IGB CarMaker to run these simulations. For the next task of randomizing all of those scenarios, we took the 100 base events and expanded them to over 1,000, trying to get at least 9 events variations for each base event. So we have this GUI that we built to run through all of those events and change parameters one at a time. You can see there we've got the lane change, start and duration times, the subject vehicle velocity profile, and then the actor position and velocity, the other actors within the simulation. So we were able to expand the list to over 1,000 events from the baseline 100. And like I say, we're able to change the major outcomes of the event from the different crash severity levels by moving the vehicles around or speeding up and slowing them down. So after we had those 1,000 events, we ran them in CarMaker, and you're able to specify these different sensors within the simulation. They have specified field of view and ranges, and you're able to match those parameters to the sensors that you're trying to model. And what they do is they grab the object within frame and extract that information and provide the output relative to what that sensor would see. Of course, these are just grabbing the perfect geometric response, so there won't be any real world responses there. So that leads us to the next task, sensor modeling, where we try to make the sensor data within the simulation a little bit more realistic. So we started that with some real world sensor testing to capture the data. We were able to leverage the smart roads and run some functional tests with actual vehicles on roads built to spec, so that we match the operational environment of the ADS vehicle while maintaining the constraints on unwanted variables with a closed course. We had 2 test vehicles, subject vehicle shown here in the picture with the sensor rack mounted on top, and then the target vehicle, which is another sedan, similar sedan, and they were fitted with GPS, and then they were all integrated into a data acquisition system that was developed for this and many other projects. So a quick overview of some of these functional tests. We have this circle track test. It's the target vehicle is traveling at along the traffic circle there at various diameters and directions and speeds. The subject vehicle is viewing it from some stationary or moving position. And then you're able to measure the response of the object at various different viewing angles and distances. So here you can see sort of the parameterized version of all of the this test, the circle track test. The next test we have is range sweep. So this is sort of, you start with the vehicles close together, and then as you go along, they open up or close the gap, and then vice versa. So here we're able to get the sort of max range of the sensor. We get a continuous response across that range, and we also see any rate effects as the velocity is either approaching or receding the vehicle. And here you can see the different ways we parameterize that: distance, velocity, rate of change, road curvature, etc. Next test we have is lane sweep. So this is mainly just to capture road information, lane lines, etc. So you can travel all across the smart roads and then do lane slaloms, lane changes, and as well as object detection of any parked pedestrian or parked vehicle. So here we have that parameterized as a different sign function traveling on the road, and at various amplitudes, velocity, frequency, offset, and road curvature. So once we capture the data in those functional tests, we need to work on extracting all the information into the target objects of interest. So with the subject and target vehicles both being fitted with differential GPS, we were able to accurately mark and bound where the target vehicle is within the point cloud of data. So here you can see we're driving down the smart road on the surface street. You can see sort of the fence line features and this building edge, and then this shadow being cast by the target vehicle in front of the subject vehicle. That's a whole lot of unnecessary data, and we're able to reduce that down into just the points that are relevant to the target vehicle by using the known location, using the differential GPS. And once we have the data relevant to the object, we're able to evaluate some of the responses here. So you can see the point clouds getting denser and denser as we get closer and closer to the vehicle, and then they decrease and get smaller. And so you can see some of the distributions of the data here as the vehicle sweeps the range. You can see we have mostly just the rear of the vehicle, but as we get closer, we're able to see sort of the top of the vehicle and side view mirrors, etc. And then at longer distances, we might get just the highly reflective points of the brake lights or the license plate. So from the distribution of data here, we'll capture that and parameterize it relative to how it responds with changes in range or field of view or different degradation intensities, and build all of the statistical distributions there. So let's see. I think it's going to play all these videos. Oh, there we go. On to the degradation tests. We used RAIN as the stand-in for degradation. You can see here the setup. We've got 2 cones of rain using the rain towers from the smart road. This is testing from another day, so this is kind of the view from vehicle if it was sitting in the rain. We did other instances where it was the target vehicle traveling through the rain, but here you get an idea of how much rain there was. And here's some of the data from these raining tests. You can see the LiDAR point cloud. It's collecting a lot of information on the ground, but once we get in the rain, it changes the reflectivity there, so we don't see much at all of the ground truth, except for maybe the retroreflective paint. Then of course the target vehicle goes from pretty dense to, once we get through the rain cloud, we start losing points on the vehicle until it turns around here and you get the broadside and you get a lot of highly reflective points. So that was the LiDAR data. We also had some radar data. This is a point cloud output radar. So significantly fewer points than LiDAR. But as we play this out, you can sort of make out the similar road features, the road edges. Here's the 2 rain towers creating a lot of noise in this area. And then the vehicle itself traveling along. Interestingly, once it's out of the rain cloud, it's able to be detected it has a lot more points to it rather, once it's out of the rain cloud, but once it's in the rain cloud, it's a little bit more shrouded. We also tested on the highway portion at higher speeds. Here you can see we get a little bit more range to the information, and as we're traveling through the rain cloud, you can see the sensor starts having this error. These 2 points here are basically the tail lights that it's picking up. So once we go deeper and deeper into the rain, the distance estimate is getting worse. It could be perhaps the time of flight effect for the LiDAR. It's going through a different medium than air, and so it might change those time of flight calculations. And since you're dealing with the speed of light, any minor difference there is going to have a big offset. So we're able to capture that error versus range effects and layer that into the statistical distribution model to add that in. And then similarly, here's the radar. You can see once we get past like the first couple of rain towers, we're not seeing much else past that, and we lose the vehicle entirely at range. And so once we collected all of that data, we needed to build the degradation model. So here is basically a flow of how we go from the car maker simulation output to the modified output. We first have to extract all the objects and make them in a usable format for us to manipulate. And likewise, we need to have a different set point that we randomize all of the input variables to, so like how much degradation we want within the simulation. So we have that built here. And then all of that gets integrated into the manipulation stack here. So we start off with object manipulation, where we can either delete or insert objects. We can modify the geometry. So if we want to test a different sensor, we can adjust the ultimate range and field of view to cut back what the sensors are, as well as do any coordinate transforms. And then we inject the noise and offset from all the different distributions we saw relative to range and degradation level. And then we add in any sort of temporal effects, so lag or rate dependencies. So starting here, we have the input degradation array. So you can see most of our events were 30 seconds long, but a couple of them ran over that up to 60 seconds. But generally, you can see they either go high to low, low to high, or are constant throughout, with either this distribution down here of being low rain or high rain. And looking at a couple of histograms, you can see here, we've got quite a few cases that are just no rain at all. And then sort of this two-modal shape of sort of a light sprinkle and then a good shower, and then a couple that are just heavy rain. This is just zooming in on those two peaks. So that's the input degradation. Next thing we have is some manipulation of the data itself, some outputs. So we've got some plots here looking at the GPS track, how we manipulated that. We added in noise, we exaggerated a bit for the plot because the distances are so large. We added in offsets to lat and long. So as we also added different cutouts. So as the sensor is going along, it might go under a bridge, or just the rain cloud is too hot, too hard for the signal to reach the receiver. So we lose the data signal entirely. And then there's some point shifts where along the way it'll lose, for example, a satellite, and so the accuracy just shifts, in an error one way or the other. We also have ACCEL data here for the IMU stack. So again, we've got different amounts of noise being added, a calibration error, which scales with higher intensity of signal, and then a bias voltage effect. Of course, with ACCELs, they have a frequency response, but since our sample rate is so low, most all of these responses are just going to be flat DC effect. Next in the IMU stack, we have GYRO data, the gyroscope. So here we had to do a little bit of integration of error. So we had like a bias voltage offset that then gets accumulated because the gyroscope integrates over time to calculate what the different 6 degrees of freedom are. So you can see all of these sort of accumulate over time in the gyro, the errors that we add in. And then lastly, here we have the some of the sensor data. These are the X distance, longitudinal distance for the different sensors we had on the vehicle. And of course, it's picking up some of the vehicle in some of them and not in others. And these are looking at oblique angles, so they see even less. But all that can be combined, and you get the full track of the object within view that's got the signal noise added to the perfect data that we get out of the simulation. All right, so now that we have all the degraded sensor data, we go on to the misinformation detection. So we start here with extracting a sort of best guess trajectory from all the different responses that we saw. And what we try to do is remove that noise that we just generated with a sliding window filter that we based off the training data, so that we can basically reverse everything we just did, so that we can know whether or not it's misinformation. The sensor data is then fused from the 7 different sensors using coordinate transform, and then like a priority filter. And basically that filter is defaulting to the front radar. And then when that drops out, it is filled with the next highest strength signal within the sensors. This helps to maintain continuity within that signal and its response traits. And then after that, the trajectory gets removed, so that all you get is the sort of characteristic response, the noise of the signal. You flatten it, and then that gets converted to a scaleogram using the coefficients from a continuous wavelet transform. So what you're left with is this plot here of the frequency response over time. And what we actually do is save that as an image, and then we add a classification label to mark the different state variables of degradation. And then we feed that into the GoogleNet convolutional neural network, and we train it according to those classification labels. And you can see here the training of the network in the bottom right figure. As we go through the different training iterations, the accuracy improves over time. And from that, with the data set, we were able to get a classification accuracy on the separate validation data set of 70.4%. Whether that's good or bad, I'm not sure. It's 70% detection of misinformation between the data that we built. We did deliberately make the data pretty challenging to the algorithm. We set it up so that the classification was relative to our baseline response model, instead of just the raw output of 100% accurate information from CarMaker. So we're comparing between 2 different, sort of noisy and slightly more noisy data sets. So it did make it harder for the neural net to decipher between those 2 classifications. And then also the event selection was deliberately made to be challenging. We selected for safety critical events, a lot of edge cases, and not just baseline vehicle driving down the road sort of scenarios. So with that, we can sort of define some future work here. We can obviously generate additional simulation scenarios. The hardest part we saw in the training of the neural net there was just not having enough data. You need a lot of data to feed a neural net, and we had to leave some for the validation data set. So getting more of those scenarios would be beneficial. However, this was a very time and effort intensive process from the beginning of the project. So next, we could look at the collection of additional types of degradation, as well as emulate like misinformation of data, whether we directly attempt to hack or spoof a sensor, or we just mess it up, put something over the lens for the LiDAR, for example, and use that to expand the classifying capability of the algorithm. And then also improvements can be made in the signal pre-processing. Perhaps we could even add like a deterministic layer that's before the neural net to handle a lot of the first order type effects, sensor dropouts and large sweeping changes can be pretty easy to extract without a neural network, and a lot of that will dominate the signal that the neural net is trying to decipher. So if we can remove and extract that before the neural network layer, so that it's only looking at the subtle differences, and that's what we use it for, then we can improve the overall effectiveness of the algorithm. And then we can work further to improve the detection algorithm. But as we stated at the top, the framework that we built to test this algorithm development, the generation of scenarios, the building of the sensor models, running it in a simulation environment, it's able to improve sort of the iteration cycles of how we develop and test and build the algorithm for the future. So with that, I think open it up to questions.
Thank you, Stephen. I believe we already have one question from Michael DeCourt. If you want to go ahead and unmute and ask your question.
Thank you. It's kind of multi-parted. I'm assuming at this stage, this is all meant to be representational, correct? Not to be used for precision modeling, especially like detection transition points for specific sensors and objects and materials.
Yeah, it was sort of like a first step in the direction of this misinformation detection. Like I say, it was sponsored by Commonwealth Cyber Initiative, so they were looking more on the cybersecurity side, and we had this experience in sensor testing and degradation development that we've worked on other projects. So kind of married the two together and seeing if we could build an algorithm that would be able to suss out the difference between, you know, sensor data and then sensor data in the rain. And there's, you know, subtle difference that we saw in some of our other projects. So we wanted to sort of challenge ourselves to see that difference. So it's a bit far off from, you know, application level, I guess.
Okay, and just kind of a follow-up, thank you. If you were not doing a cybersecurity use case, and you were doing this to be much more specific, especially right for precision modeling, and to me in those transition zones, right, like where in 50% precipitation, the little boy wearing a wool coat disappears when, or there's no usable detection data, but by sensor, right? You would need to do performance curves for each sensor with various scenarios, objects, cross sections, blah blah blah. Correct?
Yeah. And this is actually some work we did in other projects where we looked for just that, like how does a specific sensor performance change? How does its accuracy change? Its maximum detection range for different targets, so a pedestrian, a big truck, a mesh trailer, those kind of things. So we have done work in that. It just wasn't included in this project.
Thank you. Last thing, you know, I'm on SAE's ORAD on autonomous on-road driving simulation task force, and we're actually working on an appendix document to what the standard we're creating to try to specify to folks what is the ultimate simulation fidelity required for sensors, and how would you know what to look for. So I mean, you might want to join that group or whatever. You can talk to me afterwards, but just letting you know.
Oh, cool. Yeah, that sounds interesting.
Thank you.
Okay, then we have a couple more questions for you, Stephen. So the next question is, can the techniques be used for cameras?
Yeah, so we built the framework to sort of work at the object layer. So if, for example, you have a Mobileye type sensor that has all of this object level output, it can feed pretty easily through here. You just have to collect the data, build the statistical distributions, and of course the logic of how they stack on top of each other. And it should be able to feed right through.
Okay, thank you. I have another one from the audience. This is from Roger Youth. Can you, or did you go back and verify accuracy for classifications using a sensor plus specific scenarios? So should fail 30% of the time, and then essentially, did you validate the results after modeling?
Are you saying like picking, like evaluating what of the scenarios it struggled with, I guess?
So,
yeah, maybe
Oh.
Stephen, I can cover
Perfect.
it. Yeah, basically, you know, the 70% accuracy is obviously troubling, but I can believe that, knowing all of the difficulties which come into it. But essentially, did you say, okay, you know, 3 out of 10 times it should fail, so let me just pick a random sensor in one of the random difficult scenarios and go back and just check it, that, hey, this thing should fail here, you know, 30% of the time, just to validate it, you know, after you have modeled it.
That's definitely something we would want to look into. We did try changing some of the training versus validation data set to see if maybe there was, you know, certain events that were most troublesome. But we ran out of time in the project, but it's definitely something we would look into in the future.
Thank you. Okay, and I might as well ask you the other one that I asked Eric, is that could you broadly give an overview of the sensors that you tested without naming any names regarding what kind of technology they were?
Yeah, so we had the main sensors we tried to model were some of the more sort of cutting edge, I guess, in production, just out of development sensors. So the LIDAR was a solid state LIDAR. And then obviously the radar that we showed was a more advanced point cloud output, like 77 gigahertz radar, and not the older, you know, 20-ish gigahertz object output radar. So does that sort of answer without answering?
Yeah, I thought you had also used multiple LiDAR in your test, or this was primarily just.
Yeah, so we had a suite of, let's see if I can find the picture. We had a suite of sensors here, different radar. These were mainly set up for another project, but we, you know, validated across a couple of those. We built the model specific to those 2 sensors that I listed, but we looked across the different sensors to see, you know, was there a difference? And, you know, largely the LiDAR, it was just how much, you know, power it was able to send, which you're kind of limited with eye safety. And then likewise with the radar, what frequency of operation you were working at, or kind of the major dividing lines as far as how they responded to the different degradation layers. But we have a lot more detail in the degradation study we did for NHTSA. I believe it's published or in process, but yeah, that's the other project we were working on with this vehicle and setup.
Thank you.
Mm-hmm.
Thank you all. Any more questions?
So, sorry. Well, actually, sorry if I could one more.
Yes, of course.
You're saying degradation and noise. I'm curious, right? Is there a differentiation between noise and the signal being degraded because it's, you know, the signal is coming back weaker, or it's being lost at some point because of the rain? Was it some differentiation and quantification on?
Yeah, so the amount of noise in the signal is sort of like a subset of broader degradation. So you can have, as a result of the rain, you get an increase in error You might get some time latency effect, and maybe not specifically with rain. You might get a cut at the overall, max range of the sensor. So a lot of the different, spec sheet parameters that you might see would be altered from the degradation, and one of them being noise, like, a signal to noise ratio that would be an output from a radar. That signal to noise ratio is what defines like the cutoff of that's an object, that's not an object, that would show up in like the object list being spat out by the radar.
It was, sorry, and since you said it, the object, did you both care and not care about what the classification of the object was? Meaning, I know it's this car or a car or truck versus something else, and then getting any detection back that would tell you that there's an object there, but I can't classify it. Did you differentiate that?
No, we didn't go into object classification for this project. A lot of that discernment, I guess the way we use the differential GPS to seed all of the information of like, here's a broad array of point clouds. We know this is the actual object we're testing. And so we just extracted that information and got the characteristic point cloud from that. We didn't try and say this is a tall skinny thing with little appendages. It's a person. That would be sort of another layer, I guess, of complexity. I think we could probably integrate it into this process if that is a object trait. It's a classifying label with probably an associated confidence level, 0 to 100%. And that would just be another signal that gets manipulated, assuming we have that available to capture and build a model around. So yeah.
So nothing macro, like, something large versus something small. All you cared about was, am I getting back something that I might care about?
Yeah, so we only had the one target vehicle in this study, and so it was the same size every time. In the other project I mentioned, we tested pedestrian, large truck, various objects, signs, and then road markings and such. So for those, there was sort of a classification, and then we parameterized that, looking at how those metrics change versus the different test setups.
Thank you.
Thank you all. So again, thank you everybody for joining the webinar. This webinar will be uploaded to YouTube, and along with the presentation will be on our safety website. I will know everybody via email when all of that is complete. And of course, if you have any further